All right, in my haste to get to the quiz, I forgot to tell you something that is perhaps the most important thing to get out of the ANOVA part. Output that meant for you guys number 4 was true. Some future class, maybe it's not on there for you, or maybe I tell you to make sure you know it beforehand. That the correlation squared, the coefficient of determination, the quantity that gives you the percentage of the variability in the y values that is explained by the regression line. In chapter 2, where we didn't really know what that meant exactly. Here's what it means. If you take the sum of the squares for regression, which is a measure of the variability of the y hat values from y bar, from the mean of all the y's. I'll write down a formula for that in a second. And you divide it by the total sum of squares for yy. By the way, sometimes SSyy is, in this context, is called SS subtot for total sum of squares. You calculate that ratio, in this case, 4.731 times 10 to the 11th, divide by 1.34216 times 10 to the 13th. That will give you r squared. Square of the correlation, the coefficient of determination. So you can go, I guess I'll use parentheses, 4.731 times 10 to the 11th. I could use the EE thing on the calculator as well to get the 10 to the 11th. But I can also do it this way. Divide by 1.34216 times 10 to the 13th using parentheses, especially on the bottom. That's necessary, perhaps. The calculator's programmed, I'm assuming it's necessary. That ratio is about 0.035 to about 3.52%. The correlation is not very big here. R squared is not very big. Does it match? Yep, there it is. Got a match. But you should know that, and that is perhaps the most important thing to know out of this ANOVA output for this chapter at least. That r squared is SSR divided by SSE. What is the formula for SSR? It measures, it's still a sum of squares. It measures the variability of the y hat values, the predicted values from the regression line, compared to the sample mean of the y's. Y I hat minus y bar squared. We've never written down that formula before. That's called SSR, sum of squares for the regression. That's going to be high if it's a strong regression, if r is close to 1, if r squared is close to 1, r could be close to -1. If the points are almost on the regression line, most of the variability in the y values that you see, well, that variability that you see in those compared to the y bar, the sample mean of the y's, is pretty closely matched by the variability of the y hat values from y bar. Because they're close together. Y hat and y itself for each I are pretty close together. So the majority, if r squared is large, close to 1, the majority of the variation, the total variation in the y, is explained by this variation. There's not much variability about the line. The residuals are close to 0. SSE measures the sum of the squares of the residuals. And that's going to be large, as it is for this example, when there's a lot of scatter above and below the regression line. Do I have a graph for this example in here? Looks like I don't have a graph for this example in here, but I think I do here somewhere. Maybe. Maybe not. Somewhere I thought I saw one. See a graph there, but okay. And that's, oh, there it is. Okay. a lot of variability about the regression line. R squared is small. Most of the variability comes from randomness instead of the income being related to the age. I mean, the income is related to the age. Generally speaking, as the age goes up, the income goes up. But there's a ton of scatter. R squared is close to 0. 3.5%. Okay, what else should you know? Anything else with this? Get back to where I was. There we go. You should know that, again, I've said this already, these two numbers add up to this one. These two numbers add up to this one. This one is this divided by that. This one is this divided by that. This one, called the F statistic, is this ms divided by that ms. And that's the corresponding p-value for that F statistic, which you wouldn't know how to find without an F table. You should know that p-value matches that p-value. For a single variable regression, you get the same thing. You can expect perhaps a problem like you had in today's assignment, actually, where some of these could be blank and you have to fill them in. Like, for example, if you know this and that, you should be able to figure out that. A little bit of algebra. Do this minus that to get that. I'll say it again, that minus that to get that. Okay? A little bit of problem solving that way. You should be able to fill it in. Let me end our content coverage with a couple other, well, with one main new example. You're not going to have to do this on the exam because it's multiple regression, but this might be useful for you, actually. I did something useful for you. If I can find it. Multiple regression example. This would be chapter 11 stuff, which we're not really doing, but what I'm saying could be useful for you in a way I will describe. Exam data from this class in spring, can't quite see it, 2008 is what it is. I taught this class to 3 sections of about 25 students each in 2008. Wow, a lot of students. I got a lot of data about their exam scores, and this morning I took their raw data for exam 1, 2, 3, and their final exam, which was out of 126, and I massaged it. That's not messaged it. It's massaged it. I massaged the raw data. I did stuff with it, is the idea. How did I massage it? I combined exam 2 and exam 3 scores. I averaged them to get what I called exam 2 and 3 combo. To more closely match what you guys have done, having 2 exams during the semester. You had an exam 1 and an exam 2. So this exam 1 is supposed to be analogous to your exam 1. This exam 2-3 combo is supposed to be analogous to your exam 2, somewhat comparable in terms of content coverage and types of problems. Then I converted their final exam to percentages. I divided these numbers by 126 to get these numbers. And also multiplied by 100 to get it as an actual percent. You know, if you just divide by 126, this first one would be 0.9286 instead of 92.86. And I did a multiple regression using Excel Minor Analysis Toolpack. I won't show you the details, but essentially for the X's, I highlighted both of these columns. I've really got 2 explanatory variables here, and 1 response, the final exam score. I got my summary output over here. Let's take a look at the summary output and notice similarities and differences between what we've done before. This part looks the same, though there are some differences, which I will say in a minute here. This part, however, looks different. Look at that. You've got 3 rows there. Intercept, exam 1, exam 2, and 3 combo variable. That's an intercept. These are both slopes. Well, yeah, in a higher dimensional sense, they're both slopes. I'm going to show you the higher dimensional picture here in a second. 1 minute. It's probably better to think of them as rates of change. If you have too many dimensions and you can't imagine it. Based on those numbers, I got what I call the regression plane equation. This is useful for you. How? Based on your exam 1 score and your exam 2 score, you could try to use this to predict your final exam score as a percentage. The final exam probably won't be out of 100, maybe 126 or 130 or something. But as a percentage, you should be able to use this equation to predict your final exam score if, on average, the people in this class study about the same amount that people back in 2008 studied. Will that happen? I'm hoping not. I hope you study more. I'm hoping all these study tips I've given you helps you study more so you get better than this prediction would tell you. So you take your exam 1 score, whatever it was, you know, maybe it was 90. Plug it in there, multiply by 0.34627. Take your exam 2 score, which goes in the exam 2 and 3 combo for the past year, spot, multiply that by 0.61686. Maybe you got 90 there, maybe you got 80 on exam 2. Plug those numbers in, subtract 2.37103, round, say, to the nearest whole number. That would be your prediction for your exam, your final exam percentage. It's not set in stone, though. You can do better than whatever number you get. If you study hard, study harder than people do on average, you probably will do better. Okay? So this can be useful for you. Got standard errors here, t-stats, p-values that are all, well, these two p-values are small. That one's not, actually. We don't have much evidence against the null that the intercept is 0. We do have pretty strong evidence against the null that these two slopes, for exam 1 and exam 2-3 combo, are 0. We got pretty strong evidence against those null hypotheses. Not as strong as other examples we've done. No scientific notation there with negative exponents. Got confidence intervals over here. I want you to notice this p-value for that F statistic does not match any of those p-values. With multiple regression, the ANOVA part is different. It gives you different information than with single variable regression, especially with regard to this p-value. It must be a p-value for a different test then. And in fact, it is a p-value for a different test. The null hypothesis would be that both slopes are 0 for this test, both the slope for the first variable and the second one. If the slope of the first variable is beta 1 and the slope for the second one is beta 2, the null hypothesis would be that they're both 0 for this F test. And this p-value that's so close to 0 that's rounding it to 0. And the alternative would be that one or the other is non-zero. Beta 1 is non-zero, or beta 2 is non-zero. One or the other or both is what the alternative, opposite hypothesis of this one would be. And the p-value there for this test is just, again, super close to 0, not even bothering with scientific notation, just rounding it to 0. Definitely we have evidence against this null hypothesis. We're pretty confident, we're very, very confident that at least one of these two slopes is non-zero. These p-values refer to each slope individually. We've got more confidence that the slope for the exam 2-3 combo is non-zero than we do that the slope for the exam 1 combo is non-zero. Is 0. We have evidence against that. Do notice here the DF is 2. There are 74 observations. This is n minus 3 when you've got 2 explanatory variables. Also notice that with this MS theory, it's not the same as that SS because you're dividing by 2 instead of 1. So you do get something new. But this F statistic, whatever that is this ratio still. Test that. I will share this with you, by the way, for you to look at if you like. This multiple R is no longer a correlation between two variables. In fact, it's the square root of this number, where this R squared is this ratio, 7566 divided by 11906. SSR for regression divided by SS total. If you take the ratio of those two things, you get this R squared. And if you take the square root of this thing, you get this thing called multiple R, which is no longer a correlation. It's called multiple R here in chapter 11. Okay? I hope that was valuable for you to think about for the future. You might need it if you take advanced econ in particular. You might need to do multiple regression. All right, now let's spend the rest of the time reviewing. And all we really have time for is just an overall summary of topics, like we typically do. It's not necessarily comprehensive. Again, I have not written the exam yet, though I do reuse old final exam problems, and I have looked at a couple old final exams and seen what I had on there. Will I reuse every problem? Not necessarily. I might delete some or add some, but I'm going to try to quickly go through this list of topics, highlighting things that I did see on old exams that very well could show up again. Not guaranteed, but could, or maybe you might even say be likely to show up. Chapter 1, that was descriptive statistics for one variable. Mean, standard deviations, 5-number summary, maximum, third quartile, median, first quartile, minimum. Plots, the most important probably being the histogram, but also stem plots, stem and leaf plots, box plots. Should be able to do all those things. Will you have to calculate a standard deviation with a table? Probably not, but I'm not ruling it out completely. If you do, I'll tell you. Should be able to calculate them with your calculator. I think it's fairly likely that I might have you calculate the 5-number summary by ordering some data. It's a good thing to be able to remember how to do. And perhaps make a box plot. Will you have to make a histogram? I don't know. Should be able to read a histogram. That might be more likely. Making histograms takes a while. If I did have you make one, I'd maybe give you some help or something. Calculating with normal curves, we do that all the time. Both in terms of percentages and probabilities, you should be able to use good notation. If we want to find the probability that x is between two numbers, say 2 and 4, this is the notation to use, and then when you convert to z-scores, you should be able to do it for each term that you've got here. Subtract the mean, mu call it, divide by the standard deviation, sigma call it. Do the same for x, but then you just call it a z. Do those calculations, and you should be able to use this notation fine as well. Such distributions are usually modeled as continuous distributions, so it really doesn't matter in this case whether you use a less than or equal to or a less than. You still find the area under the curve with the usual method with the table. We've done so many of those, I hope that's no problem for you. But I do emphasize in looking at old exams, use good notation. I want to see good notation. And possibly pictures, I want to see some shaded diagrams of normal curves with areas shaded appropriately. Comes up again in other chapters as well. Chapter 2 is descriptive statistics for two variables, looking at for relationships between two variables. Correlation, regression, scatter plots more basically. Quantitative versus categorical variables. It does have stuff about two-way tables in chapter 2, though we didn't do it then, we waited until chapter 9. Two-way tables are for categorical data, and you can calculate proportions that are in various categories. You can make bar graphs. Identifying outliers and influential observations. All the formulas for regression. A lot of them came up in chapter 2. Not all of them, not the inference stuff. Also say there were correlation and regression cautions. The big one being correlation is not causation. I did see in an old exam there was an essay question, might be one in yours, where the heart of the reason that you should give is that correlation is not causation, perhaps, in the essay question as far as why. just because there's a correlation does not mean there's a cause-effect relationship. But then, you don't just stop there. You don't just say, oh, well, correlation is not causation. Give plausible reasons for the correlation that are not cause-effect relationships. I think an old exam for you guys, one of them was the firefighter examples. Fires with more firefighters have more damage. Does that mean firefighters cause damage? No. The confounding, lurking variable in the background, the big one, I think, is the fact that the size of the fire. If the fire is really big, there are going to be more firefighters and more damage. Okay, that's hopefully a pretty obvious one. There could be ones that are more subtle types of essay questions. There are other pitfalls as well that you should look for. Chapter 3 was about gathering data, both with surveys and with experiments. Talks about sampling also, so what is simple random sampling, using a table of random numbers. Probably I will not give you a problem where you have to use a table of random digits. It's kind of boring, it's not much to it. I did put one on an old test. But you should understand the idea of a simple random sample, and technically all our math modeling after that point assumes simple random sampling, even though that's difficult to do in practice. You kind of like after reasonably pseudo-simple random samples, it's reasonable to assume that the results of your sample don't differ too much from a true simple random sample in that kind of situation. That's where we say we do inference. Important terminology: population parameters, sample, statistics, sampling distribution, biased or unbiased, variability. Whether it's biased or unbiased is related to are you doing simple random sampling or not. Variability is related to the sample size, n. It's for sampling distributions, right? Statistics have sampling distributions. Parameters don't. Parameters are fixed but unknown numbers. Statistics are really random variables. Their values vary from sample to sample. The sampling distribution describes that variation in a probabilistic way. Find areas to find probabilities that your statistic is in various ranges. Chapter 4 gets into probability theory. What is probability? What are random variables? How do you find their means and standard deviations? For discrete ones, we had formulas. For continuous ones, you really need calculus to find the means and standard deviations. So you were just trusting me on, well, for the normal curve, for example, the mean and standard deviation formulas. Actually, we didn't calculate them. You're just given them. Though you can use, sample means and standard deviations as approximations for population ones, and then use those as your mu and sigma, for example. There's the properties, like that for example, the mean of x plus y is the mean of x plus the mean of y. The standard deviation of x plus y, if x and y are independent, was the square root of the sum of the squares of the standard deviations of x and y individually, the square root of the sum of the variances, if x and y are independent. If they're not independent, then the formula is more complicated, and we never did that more complicated formula. So those are the abstract properties. Then the important law of large numbers in the central limit theorem, talking about the sampling distribution, essentially, of x bar when n is large. Came up on a lot of quizzes. There probably will be some multiple choice on the exam, similar to old quiz multiple choice and exam multiple choice. Chapter 5, more theoretical probability, complement rule, addition rule for disjoint events, general addition rule, multiplication rule, both in general, that involves conditional probability, and the one for independent events. I did look on the old exams and saw I had one problem on an old exam at least that involved using the independent rule for the multiplication rule for independent events, where you just multiply the individual probabilities to find the probability of A and B occurring. There were the particular kind of random variables, binomial and Poisson. I did look at an old exam and saw a binomial. I didn't find a Poisson in an old one, but I'm not completely ruling it out at the moment. Bayes' rule, that was kind of complicated. I have not put that on old final exams. You did have it on exam 2. I think I probably will not put it on your exam, though there's a small chance I might change my mind. But I probably will not put a Bayes' rule on your exam. Statistical inference in Chapter 6, the basics, confidence intervals and hypothesis testing for means. Under the unreasonable assumption that we know the population standard deviation. Where did my meter stick go? Got a point here. I lost it here at the end of the semester. Didn't I have it during the lecture, right?
Fine.
Where is it?
Fine, the same.
Oh, right here? Okay, there we go. There we go. Thanks. We're assuming we know the population standard deviation to keep things as simple as possible. To focus on the main ideas. What are confidence intervals? What do they tell you? What's hypothesis testing? What's a p-value? What's an alpha level of significance? When do you reject a null or not? Type 1 and type 2 errors, power. Those are big things. All those could definitely make an appearance on the final exam. Chapter 7 was the more realistic context where we're doing the same thing. Inference for means. But now we do not assume we know the population standard deviation. We use S, the sample standard deviation, instead, which means we got to use degrees of freedom. Degrees of freedom is relevant, and then we got to use T instead of Z. You know, you always see these old exam problems that I put, state the DF if it's relevant, and don't state it if it's not relevant. It's only relevant if you use S for means. Or in Chapter 10, when we're doing T stuff with regression, then use degrees of freedom too. Do not use degrees of freedom if you know sigma, Chapter 6. Also, do not use degrees of freedom for proportions, Chapter 8. People, based on past experience, I know, seem to have difficulty distinguishing between mean and proportion problems. Chapter 6 and 7 versus Chapter 8. They are different methods. Chapter 7, it's T and DF is relevant. Chapter 8, Z and DF is not relevant. Make those kinds of mental distinctions when you start reading the problem. So you start saying, is this a mean problem or a proportion problem? Is it one sample in one population or two samples in two populations? Am I comparing means or comparing proportions? I did not put a Chapter 8 problem where you had to compare two proportions with a test on Exam 2, even though I said it could be on Exam 2. You guys? Maybe a new semester I did. Probably for Exam 3 for a new semester. That's where you have to use the pooled proportion. Since I did not put it on Exam 2 for you guys, I'm probably going to put it on the final for you guys. A comparing proportion problems hypothesis test where you've got to use the pooled proportion and the pooled standard error to ultimately calculate Z and the p-value. That will probably show up on your test. Chi-squares, Chapter 9, two-way tables. Again, the calculations are so long, I'd probably give you some help, save you some time, but you should understand the big picture. You've got the expected table. The the actual table, the data, the sample data. The null hypothesis you're testing is that there's no relationship between explanatory and response variables that are categorical. Knowing the value, so to speak, of the explanatory variable doesn't tell you any information about what to get for the response variable. You assume that's true when you do the test. You calculate the expected tables based on that, using the formula row total times column total divided by n. And then there's the formula for the chi-square. It's long. It's a summation. I'd give you some of those values. You should be able to calculate at least one of those fractions. Maybe I'd tell you what chi-squared should be, and then use the table to find the p-value approximately. Based on degrees of freedom being r minus 1 times c minus 1, where r is the number of rows going across this way, and c is the number of columns in the main part of the table, not the total rows and columns. And then Chapter 10, regression, inference, what we've been doing. Let me just end by saying, so you should look over all this stuff. This is all we've been doing the past number of days. It's all in the book, it's all in the lectures, homework. let me just mention that these formulas that I mentioned recently are the PowerPoint. This is a summary of all those formulas. By the way, I forgot to mention today, F does equal T squared. You should know that too. I didn't mention that today. I did mention it, I think, last time or the time before. The F statistic does equal T squared with simple linear regression. There's MS res. MS reg is this, divide by 1. R squared's up there. All these formulas are on the PowerPoint. There are other formulas on the PowerPoint as well. Like that, right there. And finally, let me say, don't forget about what's on Moodle. There are the old exams, including many solutions, though not all of them. And you should really study all old exams, exams 1, 2, and 3. It covers most of our content. It covers at least through section 2.1. These old exams 1, 2, and 3. With the answers. There's other exam resources if you want more problems, and those have solutions. And finally, I did add a homework to do this morning. It's way down here. Some suggested problems that you do not have to turn in that are essentially practice with the ANOVA part of the table. I've got a solution key right there. It's an Excel file. I recommend practicing at least some of those or thinking about them. And there's one more assignment to do. Not to hand in, but to do the course evaluation. Essentially by midnight next Wednesday. I'm saying it's 11:59:59 to emphasize it's on Wednesday, because midnight really is the Thursday. And it's due at the end of the day on Wednesday next week. The course evaluation. You'll get 10 out of 10 easy homework points. Shouldn't take you too long, I don't think. Do the online course evaluation. Should be an email link. Maybe from Michelle Graber. Maybe. They might be doing it differently. It's not extra credit. So it'll hurt you if you forget. So don't forget. Maybe do it right away here after class. Or after you eat lunch. Thanks for being in the class. See you Friday, 8 o'clock for the